What up? It's your boy, Sim Science. We're going to bang out a quick study guide vid. I hope you've all been excitedly preparing like busy little, what's the term? Busy little mice? Mice? I don't know. Anyway, I bet we're all excited for the test. So I'm going to go through the study guide. I'm going to do it a little differently this time though. Instead of working through every problem on the study guide, I am going to more verbally walk you through the problem, give you the starting points. I'll work through a couple of them, and I'll give you the answers to all of them. Since this is a math intensive, to some extent, it's not intense math, but work intensive test, you're not going to get credit for just the answer. So I'll give you the answer to check, because I think working through the entire problem a lot of times hurts you more than helps you. And it just kind of serves as a crutch and makes you think you get it when you don't. So let's just go through these. I'll give you the answers so you can check, and when you do your work, you can see if you're getting the right answer. And if you're not, you're going to have to analyze what you're doing and identify your mistake. And that can sometimes, in my experience, I've found, be the best teacher of how to do this stuff. So for the first one, I will do it just to give us a starting off point. So molar mass, calculating the molar mass is really at the core of pretty much everything we've done this section. So we break down our compound into its separate elements. We have one of these, we have one of these, and we have four of these. Okay, so we look at the periodic table and we see the atomic mass for copper is 63.55 AMUs or grams per mole, and then 32.06 AMUs or grams per mole for sulfur, and then this is 16 always for oxygen, or 15.99. Either way, it'll work out to about the same thing. So these we just multiply by 1 because we just have one of these, and then this one we multiply by 4, we get 64. Okay, next step is just to add them all up. When you do that, you get 159.61 grams per mole. Okay, so that's the molar mass, and we'll see here in a minute, and we should already know that this is going to be a crucial conversion factor when we're going between grams and moles, because it allows us to know how many grams are in a mole of this and how many moles we have given an amount of grams. So that is crucial. Now the second one, once you do on your own, the answer you should get is 319.22 grams per mole, or somewhere around there. Okay, now empirical formula. So we're given this. Now this question I gave you to really address what is an empirical formula. Well, an empirical formula is the lowest whole number ratio of the atoms of a compound. So if you have a compound, the empirical formula of that compound is the lowest whole number ratio. So here we have C4N2O6. Is there a common denominator, or is that the word? Is there something we can divide each of those by? Well, yeah, we can divide them each by 2. And we'll get that our empirical formula is C2NO3. Okay, so that's what an empirical formula is, the lowest whole number ratio of a compound. Okay, so then we move down to this question, which in hindsight I have some issues with, but that's okay. So solving for empirical formula, you are told that you have a compound and it has boron and hydrogen. You're given the percent boron. Some of you were tripped up on the in-class review on this type of thing. If you have the percent of one of them, you can find the percent of the other, right? It's all out of 100, so just do the math on that. And this is asking what the empirical formula is. So there's a whole process for this. It's in the foldable on page, let's say maybe 106, the foldable with empirical molecular formula. That walks you through how to do this, and we did some example problems. So you have to break it down into boron and hydrogen and go from there with a multi-step process. Now, at the end of that process, there are 2 answers I would accept for this. So the basic answer that you'll get from basically from how we learned it would be B2H3. However, the reason I say I'm kind of frustrated with myself for giving you guys this one is technically you could have done something different with the math. When we talked about if you get a half and what you do if you get a half, and in this one you don't get exactly a half, but you get to close to a half. So from what I told you, you would round to a half. If you didn't round to a half, however, you would get B5H7 because the whole point of, or not, yeah, rounding to a half and then multiplying by 2, the whole point of that is to get a whole number, whereas in this one you don't get exactly a half, and you could multiply by something different to get a whole number, which technically would be more correct. So if you got this, feel good about it. You're not going to get anything on the test that's going to trip you up. If you did the work to get this, you'll be fine. If you got this, I don't expect any of you to have gotten this. If you did, then feel really good because you have a really strong grasp of the concept. But either one of these answers, you're doing fine. Unless you got this one by doing something weird, then I just don't know. All right, now the next one, same thing, kind of. So the question for this is, what's the molecular formula? The unwritten question is that you have to find the empirical formula first. You have to go from empirical to molecular. So we did an example like that in class because to find the molecular formula, you need the empirical formula first. You need the empirical formula and then the mass of the actual molecule you have. So whereas empirical formula is the lowest whole number ratio of the atoms within an element, the molecular formula is what you actually have. So if you find the empirical formula given these percentages of different atoms in the formula, you get your empirical formula, then you need your empirical formula mass, okay? And then you need your molecular formula mass, and you do some math that you'll see in the packet or the examples, and you solve for, you get a number, and then you use that number, apply it to the empirical formula, and get your molecular formula. So after doing this, you should get a molecular formula of C2H2Cl2. Okay, so this should be your final answer for molecular formula. Now there's the empirical formula answer would be in there as well, but this is the final answer for your molecular formula. Okay, now let's move on to conversion factors. Okay, so what do you use to convert between grams and moles of a compound? So we have the conversion factor sheet in our notebook. For this one, if you have a compound, you need the molar mass to convert between grams and moles, like I talked about earlier in this video. So the molar mass is in grams per mole of a compound. That means you have X amount of grams per 1 mole. So that means you can go between grams and moles given anything as long as you drop it like it's hot and eliminate whichever one you want to eliminate. So the molar mass allows you to go between grams and moles. If you're asked to go between grams and moles, then you need to use the molar mass. What do you use to convert between atoms and moles in a sample of a pure element? Okay, so if you have a pure element, you know there's just one element in there, and you're trying to go between the number of atoms and the number of moles. Well, we use Avogadro's number, 6.02 times 10 to the 23rd atoms in 1 mole. Whatever you have, whatever type of atom you have, if it's molecules of a compound. Okay, so this could really be interchanged for particles. So whether it's atoms, molecules, whatever it may be, donuts, blueberries, you can go between the number of particles and moles by using Avogadro's number. So for every 1 mole, you're going to have 6.02 times 10 to the 23rd of whatever you have. And for every 6.02 times 10 to the 23rd particles of whatever you have 1 mole. Volume in moles. Okay, so if you have a gas at standard temperature and pressure, you're going to use the constant of 22.4 liters per 1 mole. Okay, so whenever you're given a gas, you know it's going to be 22.4 liters per 1 mole. And that's what I was looking for this. However, you could have also talked about density. So if you have the density for a compound, that allows you to go between volume and moles as well. Now, if you're using density, you're going to be given a density. So don't start thinking, oh no, if you're just given on the test a gas, you can assume it's at standard temperature and pressure unless otherwise noted, which it won't be. So you're given a gas, you know that there's 22.4 liters for every 1 mole of that gas, always, all the time. Okay, and then how do you get a conversion factor for going between moles of 2 separate substances in a reaction? So this caused a lot of confusion for you guys. But if you have a reaction, so let's do old faithful here, the formation of water. okay, you use the coefficients to go between two separate substances in a reaction for the moles. So I know that in this reaction, for every 2 moles of hydrogen, I get 2 moles of water, or for every 1, I get 1. And for every 1 mole of O2, I get 2 moles of water. And for every 2 moles of H2 that's used up, I use 1 mole of O2. Okay? So I have 3 things in this reaction, H2, O2, and H2O. These are 3 conversion factors that allow me to go between the moles of those things in the reaction. So it's just the coefficients. Okay, it is the coefficients in a reaction that allow you to go between moles. Because those coefficients represent how many moles you have to go between these things. Okay, so let's go on to conversions. All right, so this first one, you just want to break down your known and unknown, right? So your known is always going to be a number that's given to you. All right, so I know I have 24 liters of O2 gas. Okay, and we're going to assume standard temperature and pressure like I just said. Your unknown is moles of O2. So you're staying in the same thing. You just need to go between liters and moles of O2. So what would your conversion factor be to go between liters and moles? You got to figure that out, and then you just apply that. You take your known, multiply by your conversion factor oriented correctly, and then you get your answer in moles. All right, the next one, you're given 32 grams of magnesium chlorate. How many moles of magnesium chlorate would you have? Okay, so again, keeping the same substance throughout, not switching between substances. We don't need a molar ratio. You just, if you have 32 grams of this, how many moles of this do you have? So you need to start out by figuring out how magnesium and chlorate, pretty sure it's a 3, but I'm gonna double check. Yep, 3. How do magnesium and chlorate combine? Okay, you need to find the charges on these things and how they combine. And then you need to write out magnesium chlorate properly so you know, so that you can get the total molar mass. Because if we're going from grams to moles, you need the molar mass, like we solved up here. Okay, you need to find the molar mass, which allows you to go between grams and moles. And then that can be your conversion factor, the molar mass. And you can use that to go from this number of grams to how many moles you have by setting up your conversion. So it's going to be 32 grams multiplied by a conversion factor that is going to eliminate grams. And I should be putting magnesium chlorate here, magnesium chlorate, so that you can get moles of magnesium chlorate. Okay, so you need to figure out what this conversion factor is going to be so that you can do the math and get it. But notice how I dropped it like it's hot so that grams cancels and you're left with moles. Okay, now for this one, it's asking you to balance the reaction first, or I'm asking you to balance the reaction first, I should say. Okay, so you have to balance this. Ooh, that was bad. You have to balance this. Okay, and then once you balance it, I'm giving you a starting amount of lead nitrate. I say an excess of sodium chloride. I say that so that you know this isn't going to be a limiting factor. You're going to be able to react all 24.3 grams of this. It's saying how many grams of sodium nitrate can you produce? So this is a grams to grams. In other words, it's a grams of A to grams of B. So we did a lot of these, right? We did a lot of grams to grams conversions. I'm going to back up for a second real quick because I realized I forgot to give you guys the answers to these other ones. So let me see. For number 1, you should get 1.07 moles of O2. Sorry about this. Going backwards like this. For this one, you should get 0.17 moles of magnesium chlorate. I would write magnesium chlorate here, but then I'd give away how you're supposed to write it. I want you guys to be able to figure that out. Okay, so those are the, I think, yeah, these are the answers I forgot. So you should be getting this for this one, should be getting this for this one. If you're not, something's going wrong. Okay, so back to this, you're going from grams of A to grams of B. So your conversion factors, you're starting with grams of lead nitrate. Just put Ln. Now, this isn't the best practice, by the way, putting Ln in here. So, you know what, let me just do the right thing. Lead nitrate. Okay, so you're starting with grams of lead nitrate. You need to go to moles of lead nitrate. Then from moles of lead nitrate, you need to go to moles of sodium nitrate. And then lastly, from moles of sodium nitrate, you need to go to grams of sodium nitrate. So that allows you to go from grams of one thing to grams of another by using, each arrow is a conversion factor. So something to convert you from grams to moles of this, grams to moles, something to convert you from moles of lead nitrate to moles of sodium nitrate, and then something to convert you from moles of sodium nitrate to grams of sodium nitrate. So that's what you need to do there. And at the end, you should get an answer of 12.5 grams of sodium nitrate. This should be your final answer if you do it all correctly. Okay, so do it and check and make sure you're getting the right answer. Okay, if aluminum chloride decomposes into aluminum and chloride, you start with 18 grams of aluminum chloride, how many? Okay, so I'm asking you to write this reaction. So you need to be able to write out what aluminum chloride, how the charges are going to interact. What are you going to get here? You have to write a decomposition reaction into aluminum and chloride. And I'm saying if you start with this many grams of aluminum chloride, how many atoms of aluminum would there be? So I want you to pay attention to this because we did a lot of these, right? Starting with grams, going to grams. Here you're starting with grams, but you're not going to grams. So you need a different conversion factor. This is going to be the same in that you're going, so this time you're going from grams of A to atoms of B. Okay, so think about that carefully. Think about that carefully. I'm not going to write out the whole process this time because I think that would give you a little bit too much of a hint when I want you to really think. And use your mole stoichiometry island diagram from your notebook. That's a really good guide so that you can write out something like this yourself if you need to. Okay, but you won't have that in front of you in the test. Keep that in mind as well. So after doing this one, you should come up with an answer of 8.1 times 10 to the 22nd atoms of aluminum. Okay, so this should be your answer if you do it correctly. Limiting factors and percent yield. So basically this is just a simple percent yield. I gave you both answers, or both your theoretical and actual yields here, so you just have to be able to plug it in. So you always do the part over the whole. So your actual yield over what it could have been, the max it could have been, you do that, you're going to get, I think it was like 0.855 something. So you multiply by 100% to turn it into a percentage, and then you're going to get 86% yield. Okay, and then lastly, we got the big dog here. Gotta let the big dog bark, you know what I'm saying? So this thing's hard, okay, and it's kind of scrambled. I wrote this one late at night. It does make sense. It is solvable. You're able to answer all the questions here. So you have to use these percentages to do something, and then I give you the amounts of this, and you have to figure out how many molecules of calcium carbonate you could produce. You have to figure out which one's a limiting reagent, and then if you did produce this many grams of calcium carbonate, what would your percent yield be? So this brings in a lot of different stuff we did. It's pretty crazy, and that's what I want it to be like. So if you're getting the answer to this one, or the answers, I should say, to this one, you can send them my way, and I'll let you know if you're right. So if you have any questions, comment them down below. Make sure you like and subscribe, or you can email me specific questions. If one of these problems you really are having trouble with, let me know, and maybe by the end of the night or at the end of the day, I will post a video of me actually working through that problem. So let me know. Good luck, guys. Work hard, study hard, a lot of focus, a lot of energy, and I think you all have the ability to do great. I'm looking forward.